Okay, so this is the setup for part 2. We have our frequency generator. We've got a triangle wave set up at 250 hertz, so it's going linearly upward and then linearly downward 250 times a second. And so it's rapid enough that you can get a discernible signal. And so the frequency generator is connected, and let's untangle this a little bit. It's connected to the solenoid. So the solenoid has, you'll notice there's also a loose wire wrapped 5 times around the solenoid, but the solenoid itself is connected to the function generator. So you've got a triangle wave, and so the first derivative of the triangle wave should be positive, a positive straight line, and then a negative straight line. And so we have the loose wire. It's connected to 100 ohms of resistance. That minimizes the current, or that reduces the current. So we don't want too much current going through the loose wire. And you notice we've got something close to a square wave, but there's a little bit of noise in it. But the keys, you see the maximum and minimum are fluctuating a little bit, about 1 or 2 millivolts at a time. And you notice the VPP is the difference in both, or between the two. We're going to focus on that and divide by 2, but what we're going to do is we're going to take the average of 5 readings, and we're going to do that using the trigger button. And so you press the trigger and you hit OK. So the first is 14 millivolts, and so that's the induced voltage across the loose red wire. And so you got 14 millivolts, 13 millivolts, 14 millivolts, 13 millivolts, and 13 millivolts. And what you're going to do is you're going to take the average of those readings and divide by 2, because you've got a positive and you've got a negative voltage. And so that's for 250 hertz. And then you're going to repeat that for 500 hertz. So now, this is Faraday's law of induction. So the induced voltage should vary with the change in the flux with respect to time. So if you double the frequency through the solenoid, you're effectively doubling the rate at which the flux through the solenoid is changing. And which means you should be seeing a doubling of the voltage. But let's see if we actually get that. So we're going to go hit the frequency button, and now we're going to set it to 500 hertz. So now it's oscillating even faster. And so we'll see how that changes the trigger. So we're getting about 13 volts or millivolts. In theory, we should be seeing double that. So that's 22 millivolts. 25 millivolts, 21 millivolts, 24 millivolts, and 21 millivolts. So again, you'll average those 5 values together, divide them by 2, and you'll divide the average by 2. And that's what you're going to enter for the 500 hertz. So you can have one table for 250 hertz and one table for 500 hertz. So that's with n equals 5. So now what we're going to do is wrap 5 more turns around this. So 1, 2, 3, 4, 5. So we're going to use the rock as a weight, and okay, so now, we'll set this to 250 again, and we'll get our readings. So that's 26, 25, 21, 19, and 27. So again, you average those 5 and divide them by 2 because that will give you the amplitude of the voltage. And the VPP is the difference between the maximum and the minimum. Okay, so that's for 250, so we do 500. So that's 37, 34, 35, 36, and 37. Okay, so that's with n equals 10. Now we're going to increase the loops even more. So I will put this down for a second and get this right. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so now we are at n equals 15. So we'll do 250 ohms again, or hertz again. And 29, 33, 31, 35. And so, again, you take the average of those and divide it by 2. And so that's the amplitude of the voltage. And so that's the amplitude of the induced voltage you're getting. So now we're going to go back up to 500 hertz. And repeat the process. And so, okay. So that's 52, 53, 51, 50, 54. So you add those 5, take the together, divide by 5, and then divide by 2, and that gets the average. So that's with n equals 15. So now what we're going to do is add 5 more loops. So I will put this down again. So now n equals 20. So, and again, we're measuring the induced voltage through the red wire from the changing of the magnetic flux through the solenoid. So your manual, your lab write-up gives you the specifications, including the resistance of the solenoid, which is about 7.2 ohms, the length of the solenoid, the total number of turns in the solenoid, and the diameter of the solenoid, which is enough information to figure out the magnetic flux if you know the current. And so you know the voltage has an amplitude of 10 volts, and that's, so it's going from positive 10 to negative 10, and it's doing that 500 times a second, or 250 times a second. So that gives you enough information to work with. So now we're going to go back to 250 hertz, and we're going to do this again. So we've got the trigger, so that's 40 millivolts, 39 millivolts, 40 millivolts, 38 millivolts, 38 millivolts. So you get the average of those values and divide by 2, again, for the amplitude of the voltage. then we go, and this is in millivolts, not actual volts. And then we go back up to 500. And repeat the process. So that's 69 millivolts, 69 millivolts, 65 millivolts, 66 millivolts, and 65 millivolts. So that's the amplitude for 20, and now we're going to finish off with 25. So I'll put this down for a couple of seconds and wrap 5 more turns around the coil. Okay, so now we've got n equals 25, and we're going to see how that changes the voltage. And so it's been building up incrementally. So get back to 250 hertz, and so this is our last 5 readings with those. And so that's 52 volts, or millivolts, 52 millivolts, 55 millivolts, 52 millivolts, and 53 millivolts. So again, you take the average of those 5, divide by 2, and we're going to repeat with 500 hertz. So it's 90 millivolts, 93 millivolts, 94 millivolts, 92 millivolts, and 92 millivolts. So you've got 2 tables, one for a frequency of 250 hertz, one for a frequency of 500 hertz. You've got the induced voltage versus N, the total number of turns in the coil. And this is the turns in the coil of the red wire. So you're going to make your plots. Your slope should equal the change in the flux with respect to time, and you should be able to get a theoretical value from that. Again, given the specifications, you know the amplitude of the voltage and by how much it's varying per second. And you have, so it's going up to 10 and down to 0, I think is the right way. And it's doing that 500 times in a second. And so that should give you the, that's how quickly the voltage is changing. You divide that by the resistance, which is given in the lab write-up. And that's how quickly or that gives you how quickly the current is changing. And from there you can figure out how fast the magnetic flux is changing. And from there you can figure out the magnitude of the induced voltage. So a little bit of math involved in that. And as always, if you have any questions, do not hesitate to email me and ask for help. Okay, thank you very much. Don't forget, Thursday the 16th is the lab final. There's not going to be a lab class on the last week of the semester, not on the 20th or the 21st, although the lab report for this is going to be due on Monday the 20th. Okay, thank you very much. And again, if you have any questions, don't hesitate to email me, set up a Zoom chat, whatever, and ask for help. And thank you for your patience and your persistence through the semester. I know the circumstances are not easy. But again, if you have any questions, do not hesitate to email me for help. Thank you very much.